In this lecture, we will give a brief introduction to non-Newtonian fluids. Non-Newtonian fluids contain molecules with high molecular weights. Consequently, their viscosities depend strongly on the velocity gradients, and they may exhibit pronounced elastic effects, as the long molecules untangle during flow or deformation. The Navier-Stokes equations do not apply to these fluids. Instead, the analysis begins with the Cauchy momentum equation, shown here. We have the inertial term still on the left-hand side, balanced by the sum of the forces, pressure gradient, gravity, and viscous stresses due to deformation. The difference here is that for non-Newtonian fluids, the stress in the fluid is not proportional to the rate of deformation as it is for a Newtonian fluid. The constitutive relations for non-Newtonian fluids can be extremely complex, so we're going to focus only on the class of generalized Newtonian fluids, for which the viscous stress tensor takes the form shown. Tau is equal to mu times the velocity gradient tensor plus its transpose plus 2/3 mu minus kappa del dot u I. Now for an incompressible flow or fluid, this term vanishes, and we don't have to worry about the effects of dilatational viscosity or this other term here, just like we had ignored it in all previous cases when we've dealt with incompressible fluids or flows. Now the key thing here for the generalized Newtonian fluid, even though this looks like the constitutive relationship for a Newtonian fluid, the viscosity is not constant. Instead, it depends on the magnitude of the rate of strain or rate of deformation tensor. Now, unfortunately, there's a bit of a notational inconvenience, which is that for non-Newtonian fluids, typically use gamma dot as the rate of strain tensor. That's twice E, what we call the rate of strain tensor before. So E was the symmetric part of the velocity gradient tensor, so it was 1/2 del U plus del U transpose, and then potentially other terms that we neglect if it's incompressible. Now for non-Newtonian fluids, they typically use this gamma dot tensor instead, which is twice E. So the magnitude of gamma dot is twice the magnitude of E, and that's found by taking the square root of 1/2 the double dot product between E itself, or if you want the magnitude of gamma dot, you take 1/2 gamma dot tensor double dot gamma dot tensor, a lot of dots unfortunately as well in this notation, and you would get the extra factor of 2 from the square root arising here. So this is the formula used, so we're going to use this gamma dot to be consistent with the notation in most of the non-Newtonian flow literature and texts. Just recall that there is a bit of a deviation from the rate of strain tensor E that we've used before, differing only by this factor of 2. So the simplest type of non-Newtonian fluid is known as a power law fluid. For a power law fluid, viscosity takes the form mu is equal to a parameter m, which is constant, multiplied by the magnitude of the rate of strain tensor gamma dot to the exponent n minus 1. So m, as we said, is a constant with units of viscosity, and n is also a constant, and it's known as the power law exponent. If n is equal to 1, we see that we have the rate of strain tensor's magnitude raised to power 0, so mu is just equal to m. Viscosity is constant. If we have this constitutive relationship with a constant viscosity, we simply have a Newtonian fluid. Therefore, in the limiting case n equals 1, the power law model recovers a Newtonian fluid, or Newtonian behavior for the viscosity. If n is less than 1, the fluid is termed shear thinning. Because the apparent viscosity decreases as the rate of strain increases. So for example, if you stir a shear thinning fluid, shear thinning liquid faster, liquid appears to get thinner or less viscous. This is common for polymer solutions because the applied shear orders the molecules. You can think of it as untangling the polymer chains, thereby decreasing the resistance to flow. If n is greater than 1, then we have a shear thickening fluid. The apparent viscosity increases as the rate of deformation increases. So if you increase the rate of strain, you increase the rate of stirring, a shear thickening liquid appears to become more viscous or thicker. So the power law model is simplification of the actual behavior of complicated polymer solutions with non-Newtonian characteristics, but it can often be accurate over a limited range of shear rates, making it very useful in a lot of theoretical analyses. We're going to consider a slightly more complicated model of a non-Newtonian fluid in the example we're going to cover in detail for the rest of this lecture. And that is the flow of a non-Newtonian fluid or paint film on a wall. So the situation is shown here. We have a vertical wall and a film of paint of thickness capital H. Paint's bordered by the air on the right-hand side, where the pressure is simply P naught, constant atmospheric pressure. Gravity is directed downward in this figure, so gravity G is equal to G times EX because X is directed down and Y is directed to the left, so Y equals 0 at the paint-air interface and Y equals capital H at the paint-wall interface. Now we're going to assume that paint is a Bingham fluid, also sometimes known as a Bingham plastic. Bingham fluid can be thought of as a thick suspension or paste. And no flow occurs until a certain critical stress, known as the yield stress, is reached. Then the fluid flows such that part of the stream is in plug flow. For example, there's no velocity gradient. It behaves almost like a solid. In the portion of the fluid where the shear stress is less than the yield stress. If the stress is greater than the yield stress, then the fluid flows. So we can model this with this particular form of the viscosity shown here in blue. If tau, the magnitude of the viscous stress tensor, is less than this critical value tau naught, which is the yield stress, then the viscosity is infinite. The paint behaves as a solid. Infinite viscosity means no deformation. That's solid behavior. It's called a yield stress because once the stress, the viscous stress exceeds this yield stress, the paint yields. It actually begins to flow. So it transitions from a solid to liquid behavior. And we model that once the shear stress, or once the stress tau is greater than a yield stress, viscosity is mu naught, which is a constant, plus this yield stress divided by the magnitude of the rate of deformation tensor, gamma dot. These things are shown here again, reproduced on the previous page for your reference. We can see once again, tau scalar, the stress, that's the magnitude of the viscous stress tensor, and that's the square root of 1/2 tau double dot tau. This is why we introduced things like dot products and double dot products earlier in the course, so we could deal with the rheological behavior of these non-Newtonian fluids. It's also why we dealt with things like rate of strain or rate of deformation tensor in such great detail, because it becomes essential when trying to model non-Newtonian flows. So once again, a Bingham fluid is one of the generalized Newtonian fluids. The viscous stress tensor tau is similar to that for a Newtonian fluid, so it has the same form. Tau is equal to mu gamma dot, so it's equal to mu times del U plus del U transpose. So it looks just like a generalized Newtonian fluid. The thing is that mu is obviously not constant. It takes this behavior here. It's either infinite, meaning solid behavior, if the magnitude of the stress tensor is less than the yield stress, and otherwise there is flow, and it takes this particular behavior as shown. As a result, because viscosity is not constant, we have to use the Cauchy momentum equation and not the Navier-Stokes equation to analyze this flow. Now, in addition to assuming that paint is a Bingham fluid, we also make a few other assumptions about the flow. It's going to be unidirectional, steady, and fully developed, and incompressible. In other words, we assume, well, let's put down incompressible, right, as a continuity equation, del dot u is equal to 0. So we assume that ux is a function of y only, and uy and uz are equal to 0. So that's going to be the basis for the analysis of this flow, starting from the Cauchy momentum equation. So before we go any further, we want to examine the components of the viscous stress tensor tau and the rate of strain tensor gamma dot, in this case, based on our assumed form of the velocity profile. Ux is ux of y, uy and uz are 0, and see how we can simplify tau and gamma dot. We'll go through this in some detail to show the step-by-step process. The details are often omitted in texts, which can sometimes make it hard to follow upon the first introduction to these concepts. So if we look at Bird, Stewart, and Lightfoot, Appendix B1, for example, page 843, we have these components of the viscous stress tensor. Tau xx, yy, zz, xy, yx, yz, zy, zx, xz. And so, based on our assumed form of the velocity profile, ux is a function of y only, these are all velocity derivatives. So any derivative of uy will be 0 because uy is 0. So we can cross out all those terms. So here's uy, uy, uy. Moreover, it's incompressible, so we can eliminate these terms here since del dot u is equal to 0 for the incompressible flow. So our stress tensor, this part goes to 0. And we're left with mu del u plus del u transpose for the viscous stress tensor. Now uz is also 0, so we can get rid of every uz. And since ux is a function of y only, the only derivative of ux that will be non-zero is dux dy. Every other derivative is 0. So we can look at dux dx is 0, doesn't depend on x, and dux dz is 0 because it doesn't depend on z. So the only components of the viscous stress tensor that are non-zero will be these right here. So we'll get tau xy, which is equal to tau yx, is equal to mu dux dy. Every other component of the stress tensor is equal to 0. So we can write this down as a key result from examining the terms in the viscous stress tensor based on our assumed form of the velocity field. So for this problem, tau xy is equal to tau yx, which is equal to mu dux dy. So that's a very useful result that will greatly simplify our subsequent analysis. So we can highlight this. Then we can also examine the velocity gradient tensor in table A7-1. This is page 833 of Bird, Stewart, and Lightfoot. And we want to look at the components of the velocity gradient tensor that are non-zero. So once again, ux depends only on y. So every term here that doesn't depend on y, we can eliminate. Ux doesn't depend on x. Uy is 0. Uz is 0. Uy is 0. Uz is 0. Ux does not depend on z. Uy is 0. Uz is 0. And so the only one we're left with is this, right here, the yx component of del u. So in other words, dux dy is multiplied by the unit vectors ey, ex. So for the velocity gradient tensor, del u is equal to del u yx ey ex, and for what we just found here, this is then equal to dux dy ey ex. That's what it means. The yx means it's the yx component, so we take the unit vectors in the order listed, ey, ex, multiplied by this component. And this is the only one that's non-zero because it depends only on y for the x component of velocity. The other components of velocity are 0, and ux doesn't depend on x or z. So we're able to simplify del u as well. So this is a good result as well. And then from tau, we can say that, going down here, the viscous stress tensor tau is equal to tau x, y, ex, ey plus tau yx, ey, ex. We keep the unit vectors in the same order as the subscripts of the components of the stress tensor. And so based on the result here, the viscous stress tensor tau is equal to mu dux dy multiplied by ex ey plus ey ex. And then we can take our rate of deformation or rate of strain tensor, gamma dot, is del u plus del u transpose. So gamma dot is equal to del u plus del u transpose. So del u is dux dy ey ex, and take the transpose, we keep the scalar part the same, so we get dux dy. When we take the transpose of a tensor, we simply flip the order of the unit vectors here, and so we get ex ey. And so of course, gamma dot is simply 1 over mu times tau, based on our relationship over here. We already know this information, so we don't have to consider both the viscous stress tensor and the rate of deformation tensor. We only really need to consider one or the other, and then multiply or divide by the viscosity to get the other one. But I wanted to illustrate this to just make sure everyone's clear on how to take the transpose of a tensor. Alright, so the next thing I want to do is figure out what's the magnitude of the viscous stress tensor and what's the magnitude of the rate of deformation tensor. And so we can do that very simply. So let's do it on a separate sheet so we have a little bit more room. So here's tau. So if we want the magnitude of tau, which we call just scalar tau, from this it's the square root of 1/2 tau double dot tau. So we have the square root of 1/2, and we'll write tau and then take the double dot product with itself. So tau is mu dux dy ex ey plus ey ex. And then we take the double dot product of that with tau again, mu dux dy ex ey plus ey ex, and we have the square root like that. So that's our formula for the magnitude of any tensor, and we apply it to here, the viscous stress tensor. So now let's just regroup these terms. We'll do this in great detail just to make sure everyone's clear on it. So we group the scalar parts out in front, so we have a 1/2, and then we get mu dux dy, mu dux dy, so we have 1/2 mu dux dy quantity squared, and now we take the double dot products, and we simply distribute this term by term. So there's 2 terms here, 2 terms there, so we get a factor of 4 terms. So the first one here, we get ex ey double dotted with the first one here, ex ey, plus, still have ex ey from the first expression, double dot product with ey ex from the second expression. Then we have the second term in the first expression, ey ex, double dot product with the first term in the second, ex ey, plus ey ex, double dotted with the second term in the second expression, which is ey ex. Now, the way the double dot product works is we first take the dot product of the innermost unit vectors by convention, and then the second dot product applies to the outermost unit vectors. So if we take ey dot ex, that's equal to 0. So this term vanishes. Here, ey dot ey gives us 1. So we're left with ex dot ex, and ex dotted with ex also gives us 1. So this entire term here becomes 1. Next, we do the same thing here. Take the dot product of the innermost unit vectors first. Ex dot ex is 1, so we're left with ey dot ey. So this entire term here is also 1. And then finally here, we take the dot product of the innermost vectors first, ex dot ey, and that's actually equal to 0, just as it was in the first term. Ex dot ey is equal to 0 because they're perpendicular. So what we get is we get 1 plus 1, so we get 2 times 1/2, so we get 1, and then we get mu dux dy squared to the 1/2 power. So the magnitude of the viscous stress tensor is simply mu dux dy. And we'll put an absolute value here because we don't know if dux dy is positive or negative, but the magnitude of something has to be a positive quantity. And so we want to ensure that the square root gives us the positive values. We take absolute values on top of this. And we see this is exactly the same mu dux dy. That's simply the absolute value of tau xy or tau yx. And then similarly, we can proceed to find the magnitude of gamma, which is 1/2 gamma dot tensor double dot gamma dot tensor to the 1/2 power. And just as we did for this thing here, we will find that this is equal to dux dy with the magnitude. Now clearly tau is mu times gamma dot, and so if tau gives us mu dux dy, gamma dot just gives us the dux dy part. So those are both crucial bits of information, so we can summarize them here on our first sheet. So we can say that the magnitude of the viscous stress tensor for our assumed velocity field, ux a function of y only, everything else 0, tau is equal to mu times the absolute value of dux dy, and this whole thing was nothing more than the absolute value of tau yx, and gamma dot was simply the magnitude of dux dy. That's the result of actually taking the magnitude of the tensor through the double dot product as we illustrated, which hopefully is a good review of material from the first couple of weeks of the course. So now we have tau, and so we know if mu dux dy exceeds the yield stress tau naught, there will be flow, and if this is less than tau naught, there will not be any flow. So that's the key thing we have so far. So now we're going to keep progressing to analyze the flow of this paint film on the vertical wall. So the first part of this problem is determine the maximum thickness, which we'll call H equals H naught, without flow. So we recall we have to exceed the yield stress. So what happens physically? Well, the thicker and thicker this film is, the greater the influence of gravity will be. The force from gravity is going to be pulling down. So the thicker this is, the highest stress will be at the wall. So once the film exceeds a certain thickness, the weight of this film, due to the influence of gravity acting on it, will create a shear stress at the wall that exceeds the yield stress, and the paint will start to flow down. If the paint film is sufficiently thin, the weight of the film under the influence of gravity is not sufficient to induce a large enough shear stress to pull this down. When the wall exerts a stress in the upward direction to prevent the paint from falling down, the paint's pushing downward, the wall has an equal and opposite force upward, and so once the film's thick enough, as we said, the action of gravity overcomes that critical yield stress, and the paint will begin to deform. First it'll deform near the wall, and in this region here near the air, the shear stress will be less than the yield stress, and as a result out here the paint will flow like a solid. It'll be like a solid on a thin layer of liquid. So liquid will deform and flow, and then the solid will be carried along with the liquid. It's almost like water. So you have a film of ice on a wall, you heat the wall, the water melts near it, so you have liquid near the wall, it's solid ice over here, and the whole thing flows down. That's essentially what the paint film would look like based on whether or not the yield stress is exceeded. So what's the maximum thickness of the film without flow? Now there are two ways of doing this. There's the differential way from the Cauchy momentum equation, and then there's the macroscopic way by doing a macroscopic force balance. So we'll do that approach first, just to illustrate how the stresses would be computed. This is a good review of basic information we've already talked about in the course. So if we go macroscopic force balance, we'll consider a thin region in the x direction. So the same coordinate system as we have for our main figure, we just took a thin element in the vertical direction, which is the x direction going down. So we call that delta x. The thickness is h naught. That's the critical thickness. If it gets any thicker, it'll begin to flow because there'll be deformation from the weight of gravity exceeding the critical yield stress at the wall. If it's any thinner, it will not. So we're at the critical thickness, h naught. Just if we get any thicker, it will begin to deform and flow. We have paint, we have air, gravity directed down, coordinate system is the same as we had before, and I've drawn the outward normal vectors around our control volume. So our control volume has thickness delta x in the x direction, it's h naught in the y direction, and then we just assume 2D flow so we can ignore z. And we always want the outward unit normal vector. So what we can say is that at equilibrium, if there's no flow, we're under hydrostatic conditions, so the sum of the forces must be equal to 0. And we're concerned with the forces in the vertical direction. So if h is less than or equal to h naught, means tau is less than or equal to the yield stress tau naught, there's no flow, and the sum of the vertical forces must be equal to 0. So what are the forces that act on the control volume? Well, the first one is gravity, the body force. So what's the effect of gravity? Well, we integrate over the control volume rho g dv, and this would be rho g times the volume of this thing. And the volume will be h naught delta x, and let's say delta z in the third dimension to give it a units of volume. So delta z can be whatever you want it to be. It doesn't matter because it's really 2D. And we make g vector equal regular g because this is a force in the positive x direction. So gravity acts down, g is equal to regular scalar g times ex. And so if we look at forces in the x direction, the contribution of gravity in the x direction, so ex dotted with that, gives us this. Now let's look at the surface forces, or the stresses times areas acting on this. So on the top surface, we have N1. So the stress in the top surface is N1 dot sigma. And we want the x component of this, we want Ex dotted with a stress, Ex dot N1 dot sigma. N1 on the top points up, x points down, so N1 is simply minus Ex, and so this becomes minus sigma x. If we look up what minus sigma xx is, we'll see that we have contribution from the pressure. So sigma is minus p plus tau. Minus p times I plus tau. So sigma xx, we already said the only components of tau that are non-zero are tau xy, tau yz, tau xy and tau yx. So there's no contribution to the xx part. The only part here would be pressure. The minus sign gives us a plus p equals p. And the pressure in the top surface, or the pressure anywhere in this fluid, we'll see is simply the air pressure. We'll show that momentarily. For now, we'll just assume that's true. So the pressure is uniform at P naught throughout the film. And you can see that because the pressure would only change in the influence of gravity in the vertical direction, but P naught's constant along the interface through the normal stress balance. There's no variation in the x direction, and there's no reason for the pressure to vary in the y direction because that's perpendicular to gravity. So the pressure is constant at P naught, and so the force on the top surface of this control volume will be the pressure, P naught, multiplied by the surface area. The surface area is H naught times delta Z. When we look at the bottom, well, we want the x component of the stress, and the stress is N2 dot sigma. Bottom, N2 is in the plus x direction, so N2 is simply plus Ex. So you want sigma xx, which is minus P, and therefore equal to minus P naught. And so the force on the bottom becomes minus P naught times the area, H naught delta Z. Look at the right side. We want the x component of the stress. The stress is N3 dotted with sigma. N3 is minus EY. So we want minus sigma YX. So the first subscript is from the first dot product. EY dot sigma gives you Y, and EX dot that gives you X, so sigma YX. Evaluated at Y equals 0. And the pressure does not contribute to the shear stresses, only to the normal stresses, so we get minus tau YX at Y equals 0. And so we can say, well, what is the shear stress at the paint-air interface? So it's a liquid-gas interface, and so we basically say the shear stress is approximately equal to 0. 0 shear at liquid-gas interface. So finally we have the left-hand side of this control volume. So we want the x component of the stress, Ex dotted with N4 dot sigma. N4 points in the positive y direction, so N4 is plus EY. So we want sigma YX at Y is equal to H naught. And that's the same as tau YX at Y equals H naught. Now that's the stress the solid wall, we have a wall over here, exerts on the fluid because N is pointing towards the wall. And so that's going to be minus the stress the fluid exerts on the wall. And so this is equal to minus tau naught. Because at critical conditions, when this thing just begins to flow, the stress must be equal to the yield stress, tau naught. And so we have the critical thickness just where it's going to begin to flow. And so our stress at the wall must be tau naught. And it's minus tau naught because the liquid exerts a stress downward on the wall exerts the same stress upward, N points to the wall, so it's the stress the wall exerts on the fluid, and therefore it's in the upward direction to counteract the effects of the fluid on it. And so the stress here will then be minus tau naught multiplied by the cross-sectional area. So it's delta x times delta z. So now we can say the sum of the forces must be equal to 0. So we get rho g h naught delta x delta z plus the force on the top p naught h naught delta z plus the force on the bottom, which is a minus p naught h naught delta z. Then we add the force on the left hand side plus minus tau naught delta x delta z. Sum of the forces is equal to 0. The pressure forces in the top and bottom cancel because they're equal and opposite in sign. We can divide by delta x delta z. We can bring tau naught to the other side, divide by rho g, and we find, or vice versa, we can just solve for tau naught. That's what we want. So the critical stress tau naught is equal to rho g h naught. In other words, the maximum film thickness where there's no flow, h naught is equal to tau naught divided by rho g. It's a very simple result. What it basically says is, under the critical conditions, there's a balance between the critical shear stress at the wall and the body force pulling this thing down. So you take the shear stress tau naught multiplied by area, so tau naught delta x delta z, that has to equal rho g h naught delta x delta z. So the force of gravity pulling this down is balanced by the force on the wall keeping it up under the critical conditions. And so that simple balance, which we did in great detail here to illustrate how you get all the signs correct, gives you h naught is tau naught over rho g. So you could probably get this a lot faster using physical intuition from this sort of diagram without going through all the detailed work we did here, but it's good to make sure you know how to actually do this in case you need to do it for a complicated problem with a complex geometry. Alright, so that's the macroscopic approach. Now we want to discuss the sort of microscopic approach to determine the same thing. What's the minimum film thickness without flow? So let's look now at the Cauchy momentum equation. We'll look at the x component. Of momentum equation. So the x component tells us on the left hand side we have inertial terms. We have rho dux dt plus ux dux dx plus uy dux dy. I'll omit the z term because we're looking at 2D flow. This is equal to minus dp dx plus, and if we want to look at it now, we have the x component of del dot tau. So we have del dot tau. We want the x component of this. So if you look at BSL Appendix A, page 832, del dot tau x component, we get the partial of tau xx with respect to x, plus the partial of tau yx with respect to y, plus the partial of tau zx with respect to z. Now this is equal to 0. It's 2D in any case, so we get rid of that. We also have the gravity term rho gx on the right hand side. So now look at this term by term. On the left hand side, dux dt is equal to 0 because it's steady state. Dux dx is equal to 0. Ux is a function of y only. Uy is equal to 0. It's unidirectional flow. We already seen that the only component of tau that is non-zero is tau xy or tau yx. So tau xx is equal to 0. This term is non-zero. Tau yx, we've already seen, is equal to mu dux dy. And then gx x points in the direction of gravity. Gravity is g times ex, so the x component of it is simply g. So we get rho g. So what we're left with is the pressure dp dx. We're left with this term here, and we're left with the gravity term here. So we're going to say, well, what is dp dx? Well, before we get there, if we look at the y component of the momentum equation, the y momentum, we will find that dp dy is equal to 0. It's equal to 0 because y is in this perpendicular direction of gravity. Y is horizontal, gravity is vertical. So there's no variation of, no effect of gravity in the y direction, so gy is equal to 0. Every other term in the y equation vanishes because only ux is non-zero. So the y momentum equation tells us dp dy is equal to 0. In other words, the regular pressure is a function of x only. So now we can look at the normal stress balance at this interface. We can take any value of x, and at the interface, the pressure is equal to P naught. It's constant due to the normal stress balance. So as a result, the pressure does not vary with x along the interface. But we've already seen, because the pressure is only a function of x, it doesn't vary with any other coordinate. And if it doesn't vary with x along the interface, it doesn't vary with x anywhere. And so dp dx is equal to 0. Normal stress balance, P of x comma y equals 0 is equal to P naught, which is equal to constant. And because of that, coupled to the pressure being only a function of x, we conclude that dp dx is equal to 0. And so this dp dx term vanishes, just like it did when we had flow down an inclined plane. We could prove that the pressure vanishes at the interface. The same thing holds true. Even though this is a non-Newtonian fluid, the same arguments work because the y momentum equation reduces to pressure is not a function of y, it's only a function of x for the unidirectional flow. The flow is not unidirectional, not fully developed, more complicated. These arguments might not hold, but for the unidirectional flow we're considering, the pressure is only a function of x, but it doesn't vary with x along the interface because the normal stress balance says it's constant and equal to the gas pressure, and consequently doesn't vary with x anywhere. So we have a simplified momentum equation now. We have d tau yx dy is equal to, if we bring this rho g to the other side, we get minus rho g. So that's our simplified momentum equation. That's the result from the x component of the Cauchy momentum equation with the simplifications that ux is a function of y only, uy and uz are 0. This is x momentum simplified. It's a first order ordinary differential equation for the shear stress, tau yx. We need one boundary condition. So the boundary condition for this would come from the tangential stress balance. We already used it in our other analysis using macroscopic approach. Tau yx at y equals 0 is approximately equal to 0 at the gas-liquid interface. So that's the equation we need. That's our boundary condition. So now we can integrate this equation once with respect to y, since rho g is constant. If we integrate this, we find that tau yx is equal to minus rho g y plus a constant, we'll call it C1. We'll apply our boundary condition, 0 shear stress at 0 plus C1. Y is equal to 0 along the interface, so C1 is equal to 0. And we conclude that tau yx is equal to minus rho g y. So that's our integrated form of the momentum equation. So there's no flow if tau, which is equal to, we said the absolute value of tau yx, is less than or equal to tau naught. So the maximum value of tau yx occurs at the wall, where y is equal to h. So we can simply say at y equals h naught, we want absolute value of tau yx at y equals h naught, which is equal to absolute value of rho g h naught, minus. We want that to be less than or equal to the critical yield stress tau naught. And so if we take the absolute value and solve this, we find that we need h less than or equal to tau naught. And so the critical value of h naught is equal to tau naught over rho g, just as we found before. So we have the same result from either analysis if they're correct, and so the same result as before, one from the macroscopic force balance and this one from a differential analysis of the equation of motion, the x component of the Cauchy momentum equation. So we can proceed further with this part to the second part of the problem. Now that we've found the critical value of h naught, the second part of the problem is find the velocity profile if h exceeds the critical thickness. So if it's thick enough that there's flow, what is the velocity profile? So it's going to look something like we've drawn here. So here's our image again. We want to find ux of y for h greater than h naught. We have the wall at left. Y equals 0 is the air paint interface. Y equals h is the paint wall interface. The shear stress will be the largest near the wall. That's because you have the weight of the entire fluid under the influence of gravity pulling down on it. So the highest shear stress is at the wall. So the paint will be liquid near the wall where tau exceeds tau naught. It will be then solid where tau is less than tau naught. And so the transition between liquid and solid behavior in the paint occurs when tau is equal to tau naught, which is the same as when y is equal to h naught, which is the value we just found, and h naught is equal to tau naught over rho g from either of the two analyses we've already done. So now we want to consider the two regions. Liquid near the wall, where y varies between h naught and h. And then the ux will be a function of y. And then it's going to be a solid near the air, where y is between 0 and h naught, because the shear stress is less than the yield stress and it doesn't deform. So let's look now at the solid region near the air. So tau yx, we've already found that from our first part of the analysis. Tau yx is mu dux dy. And that's equal to, which we found from the second part of the analysis, tau yx equal to minus rho g y. So minus rho g y, that part came from the Cauchy momentum equation. And then this first part, tau yx is mu dux dy, that came from the constitutive relationship, or the constitutive equation for a Bingham fluid. We have to relate the stress to the rate of deformation. And this is the expression we found at the beginning of our analysis from the constitutive equation that we were given for the Bingham fluid. The only difference between this and Newtonian is that mu now varies with the rate of deformation, so mu is not constant. Now in the solid region, what is the viscosity? Well, in the solid region, viscosity is essentially infinite. So we can take mu and say mu goes to infinity in the solid region. However, the right-hand side is not infinite. It's finite. It takes on a value between 0 and minus rho g h naught. So the only way something infinite multiplied by something else can be not infinite is if the other thing is equal to 0. So in the solid region, dux dy is equal to 0. We really already knew this. We said there's no deformation. If there's no deformation, there's no velocity gradient. All the derivatives of the velocity are 0. And so ux is equal to a constant value, which we'll call u max. And that's going to be the same as the velocity at the interface between the liquid and solid regions. And so this will be ux at y equals h naught. So basically we have to analyze the liquid region and find the velocity at that interface, and then the entire solid is going to move at that same velocity as it does along the interface. The solid doesn't deform, so the velocity is constant, and the whole thing moves down at whatever the velocity of the liquid-solid interface is. So we have to figure that out by analyzing the liquid region. So in the liquid, we go back and we say mu ux dy is equal to minus rho g y. But mu, now we need our constitutive relationship for the Bingham fluid. It's mu naught plus tau naught over gamma dot. So we have mu naught plus tau naught divided by gamma dot, the magnitude of the rate of deformation tensor. And gamma dot, we've already found, is equal to the absolute value of dux dy. dux dy, we find here is negative. We want it to be positive, and it's negative because it's minus rho gy, and y takes values from 0 to positive. Viscosity is always positive, so dux dy must be negative. So if we want the absolute value of that, we want to just simply take the negative of dux dy. Also, you can look at this and say, well, velocity is 0 at the wall, it's largest away from the wall. The direction of increasing y is towards the wall, so velocity must decrease as y increases, must go towards 0 as we go to the wall. Because velocity decreases with increasing y, its derivative must be negative. And that's why another reason we need the minus sign to take the absolute value and make this positive. Alright, so now we can simply substitute and solve. So we can substitute for mu. We have mu naught minus tau naught divided by dux dy multiplied by dux dy is equal to minus rho g y. So we can multiply through on the left-hand side. We get mu naught dux dy minus tau naught is equal to minus rho g y. So we can now simply divide by mu naught, multiply by dy, and integrate. So we get dux is equal to tau naught over u minus u naught minus rho g y over u naught dy, integrate both sides, and we find that ux of y is equal to 1 over mu naught. We'll just pull that outside. Integral of tau naught dy is tau naught y minus integral of y dy is 1/2 rho g y squared plus a constant of integration, we'll call that C2. So we need a boundary condition. Boundary condition would be no slip at the wall. So in other words, Ux at y is equal to capital H is equal to 0. So we can substitute that in here. 0 is equal to 1 over mu naught times tau naught H minus 1/2 rho g H squared plus C2. And we can then solve this for C2. C2 is simply equal to 1 over mu naught times 1/2 rho g H squared minus tau naught H. So finally, we can take this expression for C2 and substitute back into our integrated expression for Ux of y. And if we do that, we find that Ux as a function of y is equal to rho g H squared over 2 mu naught times 1 minus y over H quantity squared minus tau naught H over mu naught times 1 minus y over H, if y lies between H naught and capital H. So we find that once again we substitute C2 back into here and rearrange that expression, and we get these two components. This part looks like the regular flow of a Newtonian liquid down a vertical wall. The viscosity is mu naught, and this part here is the extra effect from the yield stress from the non-Newtonian behavior. The maximum velocity is equal to Ux, where y is equal to H naught, and that's equal to rho g H naught squared, rho g H squared over 2 mu naught times 1 minus y is equal to H naught. H is still equal to H, so we have that squared minus tau naught H over mu naught times 1 minus H naught over H. And so then Ux of y is equal to U max, it's equal to the velocity of the liquid-solid interface if y lies between 0 and H naught. So in the liquid region, the velocity varies from 0 at the wall to a maximum value of U max, written out here, where y is equal to H naught. That's a transition from liquid to solid behavior for the Bingham fluid. And if you go further away from the wall than that, into this solid region near the boundary with the air, this will move downward at constant velocity since there's no deformation in the solid, so the velocity is constant. It will move down at the velocity of the liquid-solid interface, and that's equal to U max. So if y is in the solid region, between 0 and H naught, between the liquid-air paint interface and the liquid-solid interface, the velocity will be U max given here, and if we're closer to the wall, the velocity will behave here with variation in y. So this example illustrates many of the key points of analysis of non-Newtonian fluids. Many non-Newtonian fluids exhibit much more complex rheological behavior than the power law or the Bingham fluid models we discussed today, and consequently deriving results for even very simple flow situations can be quite challenging for non-Newtonian fluids. But this example illustrates the essence of it, and this is more than we need for the purposes of this introductory course.